All right, welcome to this explainer. If you've spent any time working on organic synthesis, you quickly figure out that building a specific molecule, it's honestly a lot like solving a microscopic puzzle. Today, we're zooming in on one very specific but absolutely crucial piece of that puzzle. Let's dive right in. So let's start with a core challenge that might sound familiar. What is the best way to prepare iodoalkanes? I mean, it sounds straightforward enough, right? But this is a classic hurdle when you're trying to synthesize specific organic compounds. You might have a chloroalkane or maybe a bromoalkane sitting there, but what you actually need is an iodine atom attached. The million-dollar question is, how do you get there without completely tearing the whole carbon backbone apart? Well, the elegant solution to that exact problem is known as the Finkelstein reaction. It's essentially a halide exchange method specifically used to best prepare iodoalkanes directly from their corresponding chloro or bromoalkanes. If you've been around the lab block a few times, you'll see this named reaction come up time and time again. Why? Because it's just incredibly reliable. It is the go-to move for this specific swap. And what's really fascinating here is just how beautifully simple the underlying concept actually is. Think of it like a molecular game of trading places, or maybe musical chairs. On one side, you've got your starting material, and on the other, your target product. The Finkelstein reaction essentially just acts as the mediator for a swap. The chlorine or bromine steps off, and the iodine steps right in. You don't have to rebuild the entire molecule. You literally just trade out that one specific part. To see exactly how that trade happens in practice, let's walk through the chemical equation, reading it from left to right. We kick things off with our bromoalkane. In this specific example, it's ethyl bromide. Then we add sodium iodide, represented as NaI. Now, as the reaction proceeds, the bromine and the iodine literally switch partners. The iodine swoops in and attaches to the ethyl group, giving us our desired iodoalkane, ethyl iodide, while the bromine pairs up with the sodium to form sodium bromide. It is a perfectly clean swap. Okay, so how do we actually force this trade to happen in the lab? Well, step one is easy. You combine the starting material with the sodium iodide. But step two is where the real magic happens. You have to heat the mixture in a specific solvent, usually acetone or methanol. And here is why that is absolutely crucial. Solvents like acetone easily dissolve the sodium iodide, but they force the resulting sodium bromide to precipitate, dropping right out of the solution as a solid. This neatly drives the whole reaction forward to completion. It's just brilliant design. Honestly, mastering elegant reaction mechanisms exactly like this one is what separates a struggling student from a truly successful one. And, that brings us to SHREE-EDU-SPARK. Their brand centers around this great imagery of an open book and a flame, which perfectly captures the idea of illuminating these tricky subjects. It's all about providing that essential spark of understanding you need when tackling advanced sciences. Their official tagline really hits the nail on the head: igniting minds, shaping futures. When you're in the weeds of organic chemistry, having a resource that's actually dedicated to sparking your curiosity, rather than just forcing you to memorize endless textbook pages, makes all the difference in the world. It's about understanding the deeper logic behind something like a halide exchange. Getting that fundamental why, rather than just the surface-level facts, is exactly how you ignite your academic success and ultimately shape your future. So I'll leave you with this final thought. Are you ready to stop just memorizing equations and start truly understanding them? If you want to keep unraveling the mysteries of chemistry, you can just scan the SHREE-EDU-SPARK code to continue your learning journey. Because I promise you, once you understand the actual mechanics behind the reactions, the whole puzzle just falls perfectly into place. Keep questioning and keep learning.